Every single second, all around us, there's this invisible world at work. It's the reason ice melts in your drink, but the pan you cook with doesn't. So today, we're going to pull back the curtain and make that invisible world of chemistry visible. Seriously, have you ever really stopped to think about this? They're both just simple crystals. But ice, it just sits on your counter and poof, it's a puddle. Table salt, on the other hand, needs to be heated to over 800 degrees Celsius. What's going on there? That's the exact mystery we're diving into. So how are we going to crack this case? Well, we need to shrink down, way, way down, to a level we can't see with our own eyes. Think of these virtual labs as our personal microscope, letting us zoom right in and see exactly how all those tiny atoms and molecules are behaving. Okay, first things first. Before we can figure out why some things fall apart so easily, we gotta understand how they're put together in the first place. And that means getting to know matter and its three fundamental states, or as I like to call them, its three main moods. The number one rule you gotta know about this invisible world is something called the kinetic theory. Now, it sounds a little fancy, but it's actually super simple. It just means that everything, and I mean everything, is made of tiny particles that are always, always moving. The way they're moving, well, that's the secret to everything. Let's kick things off with solids. The particles in a solid have pretty low energy. I want you to imagine a really strict classroom where everyone's in an assigned seat. They're locked into this rigid structure. They can wiggle a little bit, vibrate in place, but they are not getting up and wandering around. And that's the whole deal with being a solid. You can see it right here. The particles are held in this perfectly orderly, tightly packed structure. This rigid grid is what gives a solid its definite shape and makes it, well, solid. All right, next up, liquids. Now, the particles have a bit more energy. Picture the bell ringing and everyone pouring into the hallway between classes. It's crowded, right? People are still close, but they're sliding and flowing past one another. That's a liquid. It takes the shape of whatever container you put it in. And you can see that perfect grid we saw before is completely gone. Now it's more of a jumbled group of particles, all tumbling over each other. That right there is the molecular freedom you get with a liquid. And finally, we've got gases. The particles in a gas have the most energy of all. This is like recess time, total chaos. They're bouncing off the walls, full of energy, and spreading out to fill every single inch of space available. They'll take up whatever room you give them. Okay, so solid, liquid, gas, we got it. But things get really interesting when we start mixing them together. And that's how we end up with what scientists call solutions. A solution sounds complicated, but it's really just a mixture where one thing dissolves into another. So think about making a cool drink. The powder you pour in, that's called the solute. And the water you're mixing it into, that's the solvent. Simple as that. But here's the thing, you can't just keep pouring in powder forever, right? There's a limit. At some point, the water is just full. It can't dissolve anymore. We call that point saturation. Any extra powder you add after that is just going to sink to the bottom. So, what if you're impatient and you want something to dissolve faster? Well, turns out there are three easy tricks. First, add some heat. More heat gives the particles more energy to mix around. Second, stir it up, which physically forces everything to mingle. And third, increase the surface area. A fine powder will always dissolve faster than a big chunk, just because more of it can touch the water all at once. Okay, we have all the building blocks now. It's time to solve our big mystery. Let's get back to why ice melts so easily, while something like salt is incredibly tough. It's time to investigate their breaking points. All right, let's put what we've learned to the test. Pop quiz. I've got 3 different solids here. Silicon dioxide, which is basically quartz or sand, naphthalene, the stuff in mothballs, and cobalt chloride, a type of salt. Just by looking at them, which one do you think is the toughest? Which one has the highest melting point? The answer isn't really about the particles themselves, but about the invisible glue holding them together, their chemical bonds. Think of it like this. Some bonds are really weak, like sticky notes holding paper together. Others are stronger, kind of like magnets. And then you've got the most powerful kind, which are basically atomic superglue. So first up is naphthalene. It melts at just 218 degrees Celsius. That's because it's what we call a molecular solid. It's held together by those weak, sticky note attractions, and it just doesn't take much energy to break them apart. Next, cobalt chloride. It melts at 735 degrees Celsius. See that jump? As an ionic solid, its particles are held together by those much stronger, magnet-like forces. You need a lot more heat to break this crystal apart. And finally, get ready for this. We have silicon dioxide. It melts at a staggering 1710 degrees Celsius. Its atoms are all linked together by that covalent superglue, which creates one giant, unbelievably tough structure. This is exactly why materials like this are used to make things like cutting tools. So here's the final scorecard. It's crystal clear, right? The type of bond directly determines the melting point. And boom, that solves our original question. Ice is a molecular solid, like our mothballs, so its bonds break really easily. But table salt, it's an ionic solid, which means its bonds are much, much stronger and need way more heat to break. So, we've cracked the case of the melting points. But this stuff isn't just about a neat lab experiment. Let's see how these same invisible principles pop up in some really surprising places in our everyday lives. Have you ever seen this? You're looking at the back of a cake mix box, and it has special instructions for high altitudes. Why would baking a cake in Denver be any different than baking one in Los Angeles? Well, the answer has everything to do with the energy of water particles and the air pressure pushing down on them. Think of boiling as a battle. Water molecules are trying to escape into the air, but the atmospheric pressure is pushing them down. Down at sea level, there's a lot of air pushing down, so water has to get really hot, 100 degrees Celsius, to boil. But high up on a mountain, there's less air and less pressure. The water molecules can escape more easily, so the water boils at a lower temperature. And a lower boiling temperature means your food actually cooks more slowly. So we've seen how this hidden world of chemistry explains why salt is stronger than ice, why super tough tools are made from quartz, and even why it takes longer to cook pasta in the mountains. It really makes you wonder, doesn't it? If these tiny, invisible forces are shaping so much of our daily experience, what other invisible rules are out there, just waiting for us to discover them?